So, so I wanted to do a video on the alternating series estimation theorem because it's something that you will come across in the fall. All right, so it's pretty much it's on page 588 in the PDF, and it's mentioned in a corollary, and it says let the sum of a converging alternating series. Okay, so it's like, you did the AST test on the series, and you're like, oh, it's convergent, right? So please note this is a converging alternating series. Okay, so let's say you have S, and then B sub n is a positive decreasing sequence. So of course, like it's been proven by AST that this thing converges, right? I'm sorry, that I forgot to say converges to zero. Thought I forgot something. Yep. So then it says then the sum, the actual sum, like whatever the when you add up all the infinite amount of terms, minus this thing right here, I'll define it in a second, right? Is in absolute bars is less than b sub n plus 1. All right. So let me kind of define some things here, right, just to make sense of this, and kind of explain what exactly this thing is saying. So n is the number is the I'm sorry, it's not the number. It's the I mean, it is a number, but it's the term that. Oh, sorry. I defined this wrong. This n, this guy right here, this capital S sub n. This is going to be the sum that you get, the sum when you stop at the nth term. This capital N. So that's what this capital N means. Because, like, practically speaking, like realistically speaking, you can't go off to infinity, right? I know it's kind of like a weird concept, but we can't go off to infinity and add up an infinite amount of things. It's not possible. So we have to stop at a certain value, and we're gonna call that value capital N. All right. It could be the 100th, could be the millionth, could be like whatever, right? Any number, any finite number term. What this is saying is, if you subtract the actual, so that's what this guy is. This is the actual sum. If you subtract the actual sum from when you stop, okay, it's saying that this amount cannot exceed. It'll actually be it actually will be less than when you stop at the n plus 1th term of your sequence. Okay, when you stop at the n plus 1th term of your sequence. So basically, it's saying like the error. So this is pretty much what error is, right? I don't know if you ever seen this before. Whoops, actual minus oh shoot, or what is it? Theoretical minus experimental is like error or something like that. But it's like the actual minus where you stop is actually the error. Like how much you're off by from the real sum. And I hope that makes sense, right? Because this is actually going to come back with Power series and Maclaurin and Taylor series and stuff. So this idea hopefully makes sense to you. Let's see it in practice. Let's see what I'm trying to say here, right? So let's say I have this guy right here. It is the alternating harmonic series. All right. And we know that this converges conditionally. Oh my gosh, I didn't explain what conditional convergence was. I'll do that next class. Conditionally. Okay, so yeah, so this thing is going to converge, okay? I can't believe I forgot to explain conditional convergence. All right, so ignore the conditionally thing. We'll talk about that next class or whenever. Let's talk about this estimation theorem and how we're gonna use it. Okay, so let's say Um, let's say I want to stop at the, oh my gosh, what is wrong with me? Stop at the sixth term. So what does that mean? So this is going to be, so what's the first term? First term is positive 1, and then it goes negative 1/2, and then positive 1/3, negative 1/4, positive 1/5, 1, 2, 3, 4, 5, and then negative 1/6, and so on and so forth. Okay. What this is saying, what this theorem is saying, is if I add this up, all right, I'm really too lazy to add this up right now. But if I add this up, this is not going to be my actual term. This is not S, right? This is not what the actual sum is. It's going to be, instead, it's equal to S sub n. In fact, we can say S sub 6 because we stopped at the sixth term, right? And using the corollary or the estimation theorem, it says that the actual sum, whatever it is, I don't know what it is, right? Minus where you stopped at, okay? And once again, this means the error. This is the error, like how much you're off by from the actual sum. It's going to be less than your following term. The next, they say b sub n plus 1. So in this case, your b sub n plus 1, well, you're going to go back to your, what's my b sub n of this guy? It is just 1 over n, right? Because this is it's the alternator, and then times b sub n, right? Which is 1 over n. I should write 1 over n. 1 over n, right? So this is my b sub n without the alternator. So it's saying if I look at the seventh term, which is 1 over 7, it's saying that your error will absolutely be less than 1 over 7. You are going to be, I can't remember what 1 divided by 7 is. It is about 0.1429. So what this means is you are 0.1429 away from the actual sum, right? And hopefully this kind of makes sense. Like if we go to more and more and more terms, this number should get smaller and smaller and smaller, right? Because eventually, if you go out to enough terms, you'll be so close to the answer that it's pretty much the answer, right? So that's one way how to use the error theorem. Another way is what you can actually kind of like control how off you're going to be. Meaning, like if I said, okay, I want you to be 0.0001 away from the answer, right? You know, the question is then going to be, well, how many terms am I going to need to get that close, right? Because before it was like I went to a certain amount of terms and you told me how far away I was, but now it's like, okay, I want to be this far away, so you should tell me what term I should go to, right? And once again, it all comes down to this guy right here. So let's try that. Let me do that example right here, right? So I want to be 0.0001 away from S, meaning I want this to be 0.0001 away from the actual sum, right? So what am I going to do here? I'm going to plug in my b sub n plus 1, meaning I plug in n plus 1 into b, and I get 1 over n plus 1, right? All I did was plug n plus 1 into my sequence, and then I set this less than or equal to 0.0001. And from here, it's just algebra, right? I just have to solve for n, because this is going to tell me how many terms I need to get 0.0001 away from S. So I do some magic here, multiply both sides by n plus 1, and then, well, this is the same thing as 1 over, what is this, 10, 100,000, 10,000s? So technically, I can just multiply by 10,000, less than or equal to n plus 1, right? because I multiply both sides by 10,000, multiply both sides by n plus 1, and then I subtract 1, and I get 9, 9, 9, 9. Or 9, 9, 9, 9. What does this mean? What did we just find? What are all these 9s? What? John, explain this. Okay. What this means is I need 9,999 terms to be 0.0001 away from the actual sum. Okay, so you see in this example, we actually kind of controlled how off we were going to be from the actual answer. And we found how many terms we would need. So this means I would go back to my series here, and I would have to keep going up to the 9,999th term to be that close to the actual sum. And add up all those terms. And hopefully you guys can see this is why we need computers to do these types of computations for us. All right. So hopefully that helps explain the estimation theorem. Like I said, this idea is going to pop up with Taylor series, and this particular idea will actually come up in the fall, and you'll probably be exposed to it more in the fall. All right. Well, hope you enjoyed. Ooh, under 20 minutes. Hope you guys are proud of me. Good luck on that quiz tomorrow, and I'll see you guys on Wednesday.